Hello everyone, this is Team Maveric from Bangalore. First of all, we would like to thank Quest Global for providing us with this opportunity to exhibit our projects. The title of our project is Analytical Study of Double Wedge Airfoil for Supersonic Application and Shape Modification for Subsonic Applications. Now following are our team members. To start off, let's have a brief introduction on what an airfoil is. An airfoil is a cross-section of any lift-generating surface such as a wing, blades of a propeller or turbine. When an aircraft moves through the air, it produces an aerodynamic force. The component of this force perpendicular to the relative wind is called as lift force, and that parallel to the wind direction is called as drag force. Now the angle between the relative wind and the chord line is called as the angle of attack of the airfoil. Now based on the application, whether it is operating in subsonic or supersonic regimes, the airfoil shape differs accordingly.
Moving on to the description of our project, we designed and performed aerodynamic analysis using ANSYS Fluent on a double wedge airfoil capable of performing at supersonic speeds, that is Mach number 2.0. The airfoil was modified for subsonic applications using a shape modification technique. The modified airfoil was analyzed at Mach number 0.7. We also incorporated a blowing technique to improve the performance of the modified airfoil. The parameters for the airfoil considered were chord length of 1 meter and half wedge angle of 10 degrees. In order to validate the airfoil design, we built a remote controlled aircraft as shown in the figure. The methodology we followed was that we initially modeled the symmetric double wedge airfoil with half wedge angle of 10 degree using ANSYS software. The supersonic analysis was done for 0 degree angle of attack and Mach number 2.0. The objective of the project was to understand the flow variations, position of shock waves, and expansion waves. For subsonic applications, we modified the double wedge airfoil using ANSYS Design Modeler. This was done by smoothing the sharp leading and apex edges by creating fillets of varying radii. The model of the double wedge airfoil and modified double wedge airfoil is as shown in the figure. To mesh the domain, we used ANSYS Mesh tool. Quadrilateral elements were chosen and the quality of the mesh was ensured by having finer mesh near the airfoil and coarser away from it. For the modified airfoil's meshing, triangular elements were used so that it could fit around the curved surface. First two figures shows the mesh domain of the double wedge airfoil and the other two are the mesh domain of modified double wedge airfoil. The analysis was done using ANSYS Fluent. Density-based solver type with absolute velocity formulation was used. Viscous model chosen was a K-epsilon model and the solutions were obtained using energy equation by setting the air properties based on density.
Now moving on to the numerical calculation, using the shock expansion theory, we have determined what the coefficient of drag would be over the double wedge airfoil at a Mach number of 2.0. Now from the calculation, we have found out that this coefficient of drag is around 0.073. Now this value would be further verified using the ANSYS analysis results. Moving on to the ANSYS results. To start off, we have the lift and drag coefficient plot of the standard double wedge airfoil, which was analyzed at a Mach number of 2.0. We can see that the lift coefficient value converges at 0.0 after 388 iteration, which is justified for a symmetric airfoil at 0 degree angle of attack. Now the coefficient of drag converges at 0.07684 after 388 iteration. Now the variation of the CL and CD value with respect to the number of iterations has been represented using the table. Here we have the pressure contour and the Mach number contour of the double wedge airfoil. From the variation in Mach number, we can specify the location of the oblique shock which is present at the leading edge and the expansion wave which is present at the apex edges. Next, we have the modified double wedge airfoil. Here, the standard airfoil was modified by making the sharp edges into smooth curve by providing a fillet of radius 12 mm, 1000 mm and 450 mm respectively to the leading edge, upper apex edge and the lower apex edge. Now, from the ANSYS results, we have the coefficient of lift plot which converges at a value of 0.02976 after 1000 iterations. From the coefficient of drag plot, we have the value converging at 0.01985 after 1000 iterations and the variation in the value with respect to the number of iterations has been represented in the table. Now here we also have the pressure contour as well as the turbulent kinetic energy contour, and from the turbulent kinetic energy contour we can see that the turbulence is very limited and is present towards the leading edge, which shows an overall smooth flow over the airfoil. And at last we have the modified double wedge airfoil with the blowing port. Now blowing is basically a technique which is used to delay the flow separation or the boundary layer separation over a wing surface. This is done by producing an additional flow at certain points over the chord length. Now this in turn helps us achieve better performance. Here we have introduced a blowing port at 53% of the chord length with a blowing stream velocity of 100 meter per second. Now in order to better accommodate the blowing port, we had to decrease the upper apex edge radius to 800 mm. From the ANSYS results, we have the coefficient of lift converging at a value of 0.2776 after 1000 iteration, which is a significant improvement from the previous case. Similarly, the coefficient of drag converges at a value of 0.0237 after 1000 iterations, and the variation in CD with respect to the number of iterations can be seen from the table. Here we also have the pressure contour as well as the turbulent kinetic energy contour of the airfoil, and from the turbulent kinetic energy contour we can see that there is very minimal amount of turbulence over the airfoil surface, representing an overall smooth flow over the airfoil. Next, we will be talking about a possible material choice that would enable us to obtain the transition from the subsonic shape to the supersonic airfoil shape.
Here we are going to discuss the developments that have already been made. The matters discussed here are based on the research and studies made by the engineers at NASA and MIT. They have built and tested this new type of aircraft wing, which is assembled from hundreds of tiny identical pieces. The wing can change its shape to control the plane's flight and could provide a significant boost in aircraft production, flight, and maintenance efficiency. Conventional airplane wings are made of metal and composite materials, so they are much more heavier.
Talking about the applications of our airfoil, till date we have two commercial supersonic aircraft, that is Concorde and AAA Tu-144. Our airfoil design is a step towards making supersonic commercial aircraft a reality. Why one should consider our airfoil design when all known that the delta wing is capable of supersonic flight? Following would be few of the points that we would like to list out. Though the large surface area of the delta wing aid high lift production, it does create higher profile drag, which can be compensated for in our design. Integration of high lift devices is a difficult task for delta wing. However, since our wing plan form is similar to those in use today, this shouldn't be an issue of our design. A wing with higher sweep is more preferable to the delta wing at high subsonic speed, but the superiority of delta at supersonic speeds compensate for it. But our designs take care of this and give optimal performance even at lower subsonic speed, with developments happening into the business jet capable to travel at supersonic speed. Sooner or later we'll have supersonic passenger aircraft take to the skies.
We have used the airfoil that we designed as a cross-section of the wing on an RC aircraft modeled by us. Let us see a video of it. So what is the future scope of our work? We have established that our modification makes the airfoil effective and efficient at low speeds. It was efficient in the RC aircraft that we designed. So our further work would be to improve the performance even more. The ongoing work is the wind tunnel analysis of the airfoil and to determine parameters such as sweep angle, taper ratio when incorporated on an aircraft. We also need to determine the feasibility and ease of production of the airfoil with the choice of material that we consider. We thank you all for this amazing opportunity.